This YouTube video is an introduction to ChemActivity 19B. In this ChemActivity, we will be looking at the mechanism of electrophilic aromatic substitution. There is an animated mechanism with description available at Cal State University Fullerton at Tree Frog site with the URL here on the bottom of the page. But overall, what we've learned so far about benzene is that it is especially stable. It tends not to do reactions unless we have a highly activated electrophile, represented here by E+, and the reactions it undergoes are substitutions, in which one of the hydrogens on the benzene ring gets substituted by the electrophile. This mechanism, the electrophilic aromatic substitution, happens in two steps. In the first step, the electron-rich benzene reaches out with its pi bonding electrons to form a new bond with the electrophile. Now there's already a bond between carbon and hydrogen at this top position here. There would be hydrogen. So that after we've added the electrophile, we no longer have a benzene ring. And the adjacent carbon atom, which has only one hydrogen on it, has a net deficiency of electrons. 3 bonds, no lone pairs, formal charge of +1. In the second step of the mechanism, a base in the solution, normally a base that was associated with the original electrophile, reaches out, grabs the H+, which leaves behind a pair of electrons that reestablishes aromaticity. Overall, the original hydrogen atom has been replaced with an electrophile. Now we know that benzene is particularly stable, very stable, low energy down here, and when we do that first step, the formation of the non-aromatic intermediate, we actually lose a lot of energy. That's a very endothermic process. The only reason it will happen at all is if we have a very active electrophile, something that will attract the electrons very strongly. In the second step, however, we reestablish aromaticity, giving us a net, very exothermic step for the substitution product. It is the second step that drives the reaction to completion. Now the intermediate carbocation has, in fact, 3 resonance contributors that helps stabilize the intermediate. So here I've redrawn the intermediate from the previous slide. You can imagine that there's a total of 1, 2, 3, 4, 5 sp2 carbons, each of which has 1 hydrogen on them, and there are a total of 2, 4 pi electrons shared in the system. Now you can imagine one of the 4 electrons don't have to be localized on the 4 carbon atoms shown. You can draw a second resonance contributors by imagining one of those pairs of electrons being moved over, the second pair of electrons staying in its place, creating a positive charge opposite 1,4 from the electrophile. You can draw a third resonance contributor by moving a pair of electrons over towards that positive charge, thinking of electrons are attracted to positive charges, and the positive charge would now end up being shown on the adjacent carbon atom to the electrophile. All 3 resonance contributors are important for stabilizing the non-aromatic intermediate. Drawing these resonance contributors is important for being able to talk about directing effects of substituted benzenes as well, and so is a skill you must master in this chapter. Now we've kind of glossed over what the electrophile E+ must be. E, of course, is not a group in itself, but in fact represents some very strong electrophiles, such as a D+ from a strong deuterated acid. If whatever that electrophile is, that's what will be substituted in the final aromatic product. Here we've represented benzene or substituted benzene by putting a Z here, meaning that somewhere on the ring we have one or more other substituents, and I'm going to put that Z in the product as well, so that benzene or substituted benzenes can substitute one of their H's for deuterium with a strong deuterated acid. Another possibility is to have the NO2 plus group substitute onto the benzene ring. It is also a very strong electrophile. And when that happens, the nitro group gets put onto the benzene ring. This is exactly what happens in the laboratory this week in our nitration of methyl benzoate. Yet another possibility is to put a hydrogen sulfate group on the ring, and this happens when you take very strong sulfuric acid in the absence of water. Another common substituent for substitution in electrophilic aromatic substitution is a positively charged halide, which is made in solution by taking molecular bromine or chlorine in the presence of iron tribromide or iron trichloride, respectively. This would give a benzene substituted with a halide. And finally, there are two ways to put carbon directly onto a benzene ring through electrophilic aromatic substitution. These are the so-called Friedel-Crafts reaction, in which your electrophile is either an alkyl group, R+, alkyl cation, or an acyl cation, C double bond O, with a plus on the carbon. In both cases, these are made from the corresponding halides, bromides or chlorides, in the presence of a catalytic amount of aluminum trichloride. The acid chloride in the presence of aluminum trichloride. The products of Friedel-Crafts alkylation and acylation do involve making a new carbon-carbon bond. Okay, this chart is directly out of your Stromanis workbook. Now, when we go to do electrophilic aromatic substitutions, we can substitute benzene itself, or we can substitute rings which already have a substituent group on them. In the case of the second ring shown here, it's toluene with a methyl group shown, and the bottom ring is methyl benzoate, as we are doing in lab this week. If we were to time these reactions, we would find that given an active electrophile, benzene would react at a moderate speed in electrophilic aromatic substitution. Toluene would react faster than benzene, and methyl benzoate would react slower than benzene. Part of ChemActivity 19B, you'll be working on reasons for this, which have to do with electron donating or electron withdrawing ability, and is related to the fact that in the first slow rate determining step, the electron-rich alkene reaches out to grab the electrophile. Anything that will donate electron density will make this reaction go faster because there will be more electron density. Any group that pulls electron density away from the ring will slow the ability of the ring to grab the electrophile. There is a chart like the one shown on the bottom of this page in the Stromanis workbook, and there's a very similar one in Chapter 9 in McMurray. And what these charts will show you is that, in fact, compared to benzene, which you call the medium speed, all of the groups over here are electron donating groups, and the groups on the other side are electron withdrawing groups. And not only that, but all electron withdrawing and donating groups are not created equal. So whereas a methyl group, an R group, is a weakly electron donating group, something like an NH2 group is a very strongly electron donating group. Likewise, not all electron withdrawing groups are equal. A halogen on a ring is a weak electron withdrawing group. But carbonyl groups, such as our ester, are stronger, and nitro and cyano groups are the strongest of all. Now, in terms of electron withdrawing and donating groups, once you have a group on the ring, you have more than one possible position you can react at. For example, relative to this methyl group, you could react 1,2, 1,3, or 1,4 to put the electrophile on the ring. Likewise, on the electron withdrawing group, we could react 1,2, or 1,3, and 1,4 relative to the group we have. Note also that the remaining two carbon atoms, because of symmetry, are the same as the first two. That is, the 1,2 group over here is equivalent to the 1,2 group on the other side. Now you might expect to get a mixture of all the possible substitution products, but in fact, one or two of the possible products tend to dominate. When we run the experiment with toluene, for example, we find that we get predominantly the 1,2 and the 1,4 products, but very little of the 1,3 product. Although this is still a mixture, it's not all the possible products. Incidentally, the 1,2 products have another name. They are called ortho, and that means substitution on a benzene ring 1,2, or on adjacent carbon atoms. And the 1,4 product also has a name, para. And para means two groups that are 1, 2, 3, 4 from each other. We also find we get a very specific outcome with our electron withdrawing group. With our electron withdrawing group, we find that we get almost exclusively 1,3 product. This also has another name called the meta product. As we proceed through in subsequent class periods, we will learn how it is that the mechanism can predict that electron withdrawing groups beyond halogens do in fact direct predominantly meta, and the electron donating groups direct almost exclusively orthopara.